We've seen how the standard procedure for finding the chemical potential related to a dilute non-volatile solute can be modified to accommodate electrolyte solutes. And in particular, this has led us to mean ionic activity, A plus or minus, and its associated activity coefficient, which we call gamma plus or minus. The key that remains and the goal that remains for us is to find ways to define these that can characterize them in terms of quantities that can be measured, so that we can gain some insight into these particular solutions. Now, the first real success in doing this was some theory that was put forward about 100 years ago by Peter Debye and Electrolyte Hückel. And in essence, what they did, so let me go ahead and put the year for this. What they did was they made several assumptions. First of all, they assumed that there was an averaged potential around each ion. So it's not that there is a lot of irregularity. We're going to average the potential each ion feels and then treat every ion as though it's feeling that same kind of potential. We're also going to assume that their potential fields, that is, the ones associated with each ion, are independent of one another. So they are, in some sense, you can think of this as being kind of an idealized model, idealized approximation, that they're all independent of one another, so they're all acting independently as well. All right, we're going to also assume, or they assumed, that these solutes, the ionic solutes, completely dissociate into ions. Now, this isn't to say that every single one, that it forms a strong electrolyte necessarily, but all of the ones that do dissolve separate into ions. None of them enter into solution without separating into its ions. We're also going to utilize the approximation that the ions are point particles. That is to say, they have no volume. And then finally, that the assumption of their theory was that the non-ideality of the electrolyte solutions, and we talked about that in one of our videos, the non-ideality arises solely from the electrostatic forces. That is to say, their strength and their range are the things that really distinguish these kinds of solutions from one another. Now, I'll say that with this set of assumptions, there is an inherent limitation that this is always going to be limited to dilute solutions. As soon as we have a non-dilute solution, then, for example, it's much more difficult to make the case that that the potential fields are independent of one another, that they can act upon some averaged potential. There's also some work that they did in treating the solvent as though it were a continuous field, and as soon as you have a very strong concentration now, it's, I'll say, a little less valid to make that assumption. So all of the results we're going to talk about are limited to dilute solutions. And in fact, this represents a limit to the applicability of the theory, and that's why this is sometimes called the Debye-Hückel limiting law, is because it's limited to dilute solutions. All right, so what can we say about this? I'm not going to take you through a full derivation of it. I'm not sure that I could do a full derivation of it for you, but I want to talk about a few particulars. Okay, so we have a point particle here that is an ion. And so part of what they are establishing is that this ion has some region around it in which it is exerting its electrostatic force. And so this region that it's prevalent in is going to be referred to as its ionic atmosphere. And so this is sort of the first target of the Debye-Hückel theory, was to define this and to establish something that was related to the size of this ionic atmosphere, which was related to a parameter they called kappa. And this kappa has a unit of 1 over length, so 1 over kappa is essentially the effective ionic radius for this. This kappa, by the way, is also called the Debye length. All right, so the first step of their theory is to model the ionic radius, if you will, the effective radius that each ion is exerting on the particles around it. And when in going through their formalism, they ended up deriving an expression that looks something like this. They derived an expression for kappa squared, and it was equal to a sum over the various charged particles. That is, this sum is just over the charged particles produced by one solute molecule. And it is related to the charge of that particle squared, and then divided by the permittivities of the vacuum and the solvent, and then some familiar pieces, kBt. And then this was then multiplied by the number density of these particles in that solution. All right, so this was the expression that they derived for this Debye length. And I'll just say that it's a little bit more convenient when instead of using number density, one uses a concentration. So in fact, one can convert this to do a concentration, say in molarity, by writing it like this. We'll have 1,000 in units of inverse molarity times Avogadro's number. And then I'm going to include all of these constants down here, epsilon 0, epsilon r, kBt, and then we'll have a sum, and this sum will be now of the charge squared times the concentration of the ions in the solution. So we have all of the stuff that is summing over the ions that are produced when a solute particle dissolves. Okay, I want to specify once again, epsilon 0 and epsilon r are dielectric constants. So these are well-known constants. Epsilon 0 is for a vacuum, and epsilon r is the dielectric constant for the solvent. And for water, it's something like 78.5. All right, so I can't tell you, I don't know off the top of my head what it is for a vacuum. And of course, then this is also tied to the temperature via the Boltzmann constant times the temperature. All right, now this thing that appears over here actually appears in a lot of the elements of the theory. And so one of the things that they did was to define a new constant, and I'm going to write this in red especially. I'll call it I sub c, which is essentially 1/2 the sum qj cj, qj squared, which is going to be, and I'm going to divide this by e squared, so that this becomes 1/2 the sum of z sub j squared cj. And this z sub j is just the net charge on that particle. Okay, it's the charge number. And actually, I've written this backwards. The charge on the particle is zj times e. We've divided out the E dependence, E being the electron charge. All right, so this quantity here is something that is defined to be the ionic strength of the electrolyte solution. All right, so it's going to be something, again, if we have, if we have a 1,1 electrolyte, each of the z's is going to be 1, so it will just be the sum over 1 of the positive ion concentration and the negative ion concentration. And since both of these are going to be the same as the regular concentration, it's just equal to the concentration of the ionic solute in the solution. All right, so it'll be different, though. You should be aware it'll be different. For example, for a 1,2 electrolyte or a 2,1 electrolyte. Anything that's not a 1,1 electrolyte is going to have different values of Z here, and so they'll end up being different. And in fact, for a 1,2, you can show that it's equal to 3 times the concentration of the solute in molarity. All right, now let's look at the second part of their theory, but I'm going to need a new page to do this. Okay, the second page is actually about how to evaluate the activity coefficient in terms of this Debye length that they have used in deriving this. And what they find is that this plus or minus gamma, the log of that, can be written as follows. We can write it as minus the product of the charges, absolute value, times the Debye length divided by now a very similar set of constants that we saw before. Remember that before we were talking about kappa squared, and this is just kappa. All right, so if we were to use the definition of kappa in terms of the ionic strength, we could actually write this somewhat more directly in terms of something that would represent, for example, since kappa squared is proportional to the ionic strength, kappa here means that this would be proportional to the square root of the ionic strength. So in fact, what we would find is that this log of the activity coefficient is proportional to, and instead of writing this in terms of the charges, I'm going to write it in terms of the charge numbers, charge coefficients, Z plus and Z minus. So it's proportional to this times the square root of this ionic strength. All right, and this is the applicable part of this theory, that we can calculate this quantity, the ionic strength, and with the values of the charge numbers associated with the ions that are produced in the solution, we can derive, in essence, the activity of the activity coefficient for the chemical activity. Now, a couple of things that I want to mention here, and one is that a lot of the solutions use as a solvent water. So it's useful to know some of the shortcut formulations that one can use when you have water as your solvent. For example, the quantity 1 over kappa, the Debye length, can be written as 304 picometers divided by the square root of the concentration in molarity. So this is in molarity. All right, so this is a very helpful thing to derive the Debye length. And this, in fact, could be used in this formula if one wanted to go ahead and plug in these permittivity constants. One could use that directly to determine the log of the activity coefficient. However, there's an easier way to do this, and that is for water, one can write that the log of the activity coefficient is equal to minus 1.173 times this product of charge numbers times the square root of the ionic strength. And so this gives us a very handy formula for evaluating these things. I should note that IC here is in units of molarity. Okay, because remember, it is its definition is given where? Its definition is on the previous page. Okay, but its definition of Zj squared times Cj, the Cj's here are in units of molarity for this particular formula. If you would prefer to use molality it turns out the formula is very similar, but the constant here would be minus 1.171 if concentration is in molality. All right, so good operational equations to use can be used in solving problems. I think that the most important thing for you to get from this particular part of the lesson is that what Debye and Hückel did was to apply some very simple approximations and assumptions to get to a very general result, albeit one that only works for dilute solutions.